Welcome to Friday Happy Math Hour. Today I'm going to go over basic matrix operations and inverses. Okay, so for basic matrix operations, I'm going to start with a real life example, then determine the dimensions or the size, matrix addition, matrix subtraction, a scalar multiplication, and application problems. And then afterwards, I'm going to go over matrix multiplication, the identity matrix, and inverse matrices. Okay, to begin with, matrices. Matrices are important in the fields of management, natural science, engineering, and social science as a way to organize data. Example 1. Furniture manufacturing. Say the Easy Life company manufactures sofas, armchairs, in 3 models A, B, and C. The company has regional warehouses in New York, Chicago, San Francisco. In its August shipment, the company sends 10 Model A sofas, 12 Model B sofas, and 5 Model C sofas, 15 Model A chairs, 20 Model B chairs, and 8 Model C chairs to each warehouse. How can we organize this data? This data might be organized by listing them as follows. Sofas, 10 Model A, 12 Model B, and 5 Model C, right? And I got them from right here. 10 Model A, 12 Model Bs, and 5 Model Cs. And the chairs are 15 Model A, 20, and 8. Or we can organize it in a tabulate form, which is this is the furniture here, right? And this is the models. So for example, sofas, we have Model A, which is 10, Model B, which is 12, and Model C, which is 5. And with the chairs in the same process, we have 15 Model A, 20 Model B, and 8 Model C chairs. Okay, now this can be done in a matrix. Matrix M is 10, 12, 5, right? And I got them from here, from the sofas, and 15, 28. My rows, right? These rows represent the furniture, right? This is the furniture here, right? Which are the rows. And the columns represents the model. Model A, Model B, and Model C. That's an example of how we can use matrices in real life. But I'll cover more examples later on during this PowerPoint, but in the meantime, let's see how we can organize matrices. Okay, a matrix. This is called matrix A. Matrices are denoted by capital letters, right? Or uppercase letters are used to name matrices. Example, this is matrix A and matrix B. And if you notice, the lowercase letters are used to name the elements. All these are elements, right? This is element 1, sub 1, 1, which means this is the first row and first column. Okay, I think I'm jumping the gun a little bit. Let me see here. Lowercase letters are used to name the elements of the matrix. Example, elements A for matrix A and elements B for matrix B. Okay, I was jumping the gun. Okay, here we go. For example, this is matrix. This is matrix A. This is row 1. Row 1 means right, because this is matrix A, uppercase, right? And this will be the lowercase. This means first row, first column, first row, second column, first row, third column. So the first number represents the rows, and the second number represents the columns. And then here, right, in row 2 is going to be A21, A22, and so forth. Okay, and this can go up to like many rows and columns. Okay, but here that's why it goes to M, which is the rows, and N, which is the columns. These are called the positions of an element. Okay, so for example, A11 means, I just mentioned that, 11 means position is row 1, column 1. A14 means row 1, column 4. A23 means position is row 2, column 3, right? Row 2, column 3. Okay, now this is matrix A. What is the position of the following elements? Okay, please participate here, guys. I want to make sure that you understand what I just went over. And this on this PowerPoint, I'm going to go a little bit slower than before because I want to make sure that you guys understand what I'm trying to explain. Okay, so for example, can somebody put in the chat what's the element A13? Anybody? A13? What number is it, or what element is it? I'll give you guys a hint, right? The 1 is the first row. The second number, the 3, is the third column. So the answer should be 3. Okay? Now, how about this one here? A24. Can somebody tell me what the number is? Anyone? Very good. Very good, my friend. The answer is 8. Okay? Okay, now comes the matrix dimensions or the size. Rows by columns, right? So the first is going to be the rows in the columns. Number of rows, X, number of columns, right? So then, here we go, is number of rows times number of columns. So for example, these are 2 rows, right? 2 rows, and 4 columns means it's a 2 by 4 matrix. Example 2, determine the dimension of the matrices. Okay. For example, this will be a 3 by 3, right? Because we got 3 rows and we got 3 columns. Can somebody name the second matrix, the size of it? Anybody? Patricia, did somebody put something there?
Yes, sir. Jacob says 1 by 3.
Okay, Jacob, how many rows are there, my friend? It's going to be 3, correct? Let's see here. Let me check at the chat. Yes, yes, Jacob, it's going to be 3, right? So it's going to be a 3 by 1, my friend. Very good, 3 by 1. Okay, how about this one here? This will be, I'm sorry about that, this will be a 1 by 3, right? Because the first are the rows, and the second one will be the column. So this one here will be 3 rows and 1 column. And the third matrix is going to be 1 row and 3 columns. Hey, students, this is crucial for you guys to know. Why? Because in order for you guys to add or subtract matrices, they have to be the same size. And when you multiply, it's a specific order that they have to be in order to do the operation for multiplication. Okay, but I'll cover that once we get to multiplication. Okay, now, can somebody tell me what this one is? How many rows? One, 2, 3, 4, right? So it's 4 by 2. Very good, Jacob. Very good. Okay. Now here comes matrix operations. Okay, now, again, this is matrix A, right, and matrix B. So in order to add or subtract, right, in order to add or subtract matrices, the matrices must be the same size. If they're not the same size, you cannot do the operation. Okay. So for example, matrix A plus matrix B. Right, so say that we're adding, right, say these are the same matrix, same size. So we're going to add this position, A11, which means A, first row, first column, plus B, first row, first column. Right, and then we're going to add the first row, second column from the A matrix, and the first row, second column from the B matrix. And the pattern continues, right, until we get to the size of the matrix. And then, right, and then comes the second row, right? For each one, second row, first column, plus second row, first column, for each, for each position there. Okay, and you keep doing that until you add the last position. That's why it's called AMN plus B. The M stands for the rows and the N stands for the columns. Same thing here, right? AMN plus B NP. This one has NP. The N stands for the rows here, and the P stands for the columns. Okay, the notation, the notation at times for the matrix, they use. For example, here the sum of the two M by N matrices X and Y is a M by N matrices, in which each element is the sum of the corresponding elements of X and Y. All this means, guys, is what we did here. Okay, we're going to add them, like I said, first position here, first row, first column on A matrix plus first row, first column on B matrix, and you continue until you're done with the matrix. Okay, now for the difference, it's the same thing, but instead of adding, it's going to be subtraction. Okay. Now, here are some examples. It's always good to do examples so the students can understand. Okay, now, first of all, let's start by naming the matrix. Matrix A is a 2 by 3, right? We have 2 rows and 3 columns. Matrix B is also a 2 by 3. We have 2 rows and 3 columns. Matrix C is a 2 by 2, and matrix D is a 2 by 2. So let's do A plus B. So A plus B, we're going to get, right, the first A11 plus B11, 1 plus 8. And then -3 plus 0. And then 2 plus 1. And then we're done with the first row. And then we continue with the second row. It's going to be 2 plus -1. And then 2 plus 3. And then -1 plus 4. And then all we do is add them. That'll be 9, -3, 3, 2 plus -1 is 1, 2 plus 3 is 5, and -1 plus 4 is 3. Okay, now, if you want, right, because most of the times the homework is done on my math lab. If you want this step, you can skip it, right? You can skip this step. You can just go, but be real careful that you're doing it right. You can go 1 plus 8 is 9. -3 plus 0 is -3. 2 plus 1 is 3. 2 plus -1 is 1. And 2 plus 3 is 5. And -1 plus 4 is 3. I did it like this, guys, by showing the work, just so you guys can see exactly what's taking place. Okay? Now let's do C plus D. So first of all, can we do the operation? Yes, we can, right? Because they're the same size. When they're the same size, we can add them or subtract them. So C plus D will be 5 plus 2, and then 1 plus -1, then -4 plus 9, and 3 plus -7. The result will be 7, 0, 5, and -4. That's my answer when I add matrix C plus matrix D. Now, how about A plus C? A is 2 by 3, and C is 2 by 2. So this cannot be done because they're not the same size. Okay. Okay, now let's continue. Are you guys okay? If you guys okay, guys, put like a thumbs up on your screen. That way I know I can proceed. You guys okay? Anybody else? Are you guys okay? Can I continue? If you guys need help, guys, afterwards there'll be tutors to help you. Okay, say for example you don't want to say right now that you understand it, that's okay. But please, guys, try to get some assistance if you guys are lost. I'm trying to do I'm trying to do the best that I can with this PowerPoint so you guys can understand the procedure. Okay, But anyway, let's continue. Now comes the subtraction. Again, the 2 by 3 matrix. 2 by 3 is also B, and C is a 2 by 2, and D is a 2 by 2. So A minus D. So it's going to be 1 minus 8. Negative 3 minus 0, and 2 minus 1. And then on the bottom, on the second row, we have 2 minus negative 1. We got 2 minus 3. And we got negative 1 minus 4. Right? So then we can add them. Subtract them. 1 minus 8 is negative 7. Negative 3 minus 0 is negative 3. 2 minus 1 is 1. 2 minus negative 1, right? Remember, when you have two negatives back to back, this becomes addition, so it'll be 3. 2 minus 3 is negative 1. And negative 1 minus 4 is negative 5. Now let's do C minus D. So C minus D is going to be 5 minus 2. 1 minus negative 1. Negative 4 minus 9, and 3 minus negative 7. Okay, now, hey guys, another way you can do this one, the subtraction is like this. I think it's better when we guys add. So if it's minus, you can switch all the signs on each element on the D matrix. You see, for example, right, this negative 1 would have been a plus, right? Because negative will be a plus. This would just be a negative 2. This one here will be a negative 9. This will be a positive 7. You see, it's going to turn to 7. You can do it that way, convert it to addition instead. But anyway, you get the same answer. There'll be 3. There'll be 2. There'll be negative 13. This will be positive 10. Okay. Now, can we do A minus C? A is a 2 by 3. And C is a 2 by 2. If you notice, these are not the same size, right? So this is not possible, or it cannot be done. Not the same size. Okay, let me continue. Now this is called the scalar multiplication. The product of a scalar K and a matrix X is a matrix KX, in which each element is K times the corresponding element of X. So for example, this is what it's saying here. Say this is X, matrix X. You want to find 6X, right? And remember, capital letters represent matrices. So 6X is the same thing as 6 times every element in matrix X. So it's going to be the same thing as 6 times 2, 6 times 0, 6 times 5, 6 times 4, 6 times negative 2, and 6 times negative 3, right? And then after you do the operation, it's going to give us 12, right? 0, 30, 24, negative 12, and negative 18. All right, guys, this step, like I said earlier, this step, you can skip it. But again, I just show you what's taking place. But you can go like this. 6 times 2 is 12. 6 times 0 is 0. 6 times 5 is 30. 6 times 4 is 24. 6 times negative 2 is negative 12. And 6 times negative 3 is negative 18. Okay? Okay, now, remember earlier that I put when you subtract two matrices, right? So for example, if we had like a matrix minus matrix X, this is like a negative 1 here, right? There's a negative 1, but it's not visible, right? Because we know it's like negative 1. So in other words, right, if we have the matrix X is 2, 0, 5, 4, negative 2, 3, right? All we do is multiply them out, right? Or if you notice, switch the signs. Negative 2, that's 0. That'll be negative 5, right? That'll be negative 4. That'll be 2. And that'll be 3. When you have subtraction, you can convert it to addition by switching all the elements inside the matrix to the opposite sign. or you can just go -1 times each one of those, each one of those elements. Okay. Okay, now on example 6, we have 1, 2, and 3, right? We're going to work at 3 problems. So on 1, it says -4 times 8. There's -4a, right? So this is my A matrix. So I'm going to multiply -4 times every element in matrix A. So -4 times -2, -4 times 0, -4 times 5, -4 times 3. And then, so this is my result, right? Or you can go like this, right? This is to show the work. Or you can go -4 times -2 is 8. -4 times 0 is 0. -4 times 5 is -20. And -4 times 3 is -12. Okay, so this is my result. Now let's try 2 for example 6. This is 5b, right? So 5b is the same thing as 5 times matrix B. Matrix B is 0, 2, 4, -6. So in the same manner, we can multiply the 5 times every element in matrix B. Okay? And like I mentioned earlier, this if you want, you can skip it. You can go straight from 5 times 0 is 0. 5 times 2 is 10. 5 times 4 is 20. And 5 times -6 is -30. Okay? Now comes example 6.3. If you notice, -4a, right? I did it in 1, which is 8, 0, -20, -12. And 5b is done in example 6.2, which is 0, 10, 20, -30. So then, right, so -4a, right, was 8, 0, -20, -12. Plus the 5b was done in 2 here. So it's going to be 0, 10, 20, -30, right? So now we do what we did earlier. Okay, again, it's going to be 8 plus 0, 0 plus 10, -20 plus 20, and -12 plus -30. Or you can go like this. 8 plus 0 is 8. 0 plus 10 is 10. -20 plus 20 is 0. And -12 plus -30 is -42. This is a result for number 3, which is -4a plus 5b. Okay. Okay, now let's continue now. Now here's where the matrix application comes in. Because remember the first I think it was the second slide that I showed you. Okay, this is the example again. Okay, guys, the same example as before. We call the example of furniture manufacturing. Remember, this was sofas and chairs for model A, B, and C. Remember that? Okay, now here they're saying the first sentence or the first 2 sentences was from the second slide. Okay, now this will will be for C. In its August shipment, the company sends 10 Model A sofa sets, 12 Model B sofa sets, and 5 Model C sofa sets. Okay, 15 Model A chairs, 20 Model B chairs, and 8 Model B chairs to each warehouse. Okay, so the C stands for Chicago. Okay, and this is the shipment that was sent to Chicago. Okay, now during August, the Chicago warehouse of VZ Company shipped out the following numbers of each model, which the entries in the matrix have the same meaning as given earlier, right? So then these, the K means these were shipped out. 5, it was 5 Model A sofa sets, 10 Model B chairs, and 3 Model C chairs, and over here is going to be sofa sets. My bad. And 13 Model A chairs, 12 Model B chairs, and 8 Model C chairs. Right? That's what was sent out. So what was Chicago's warehouse inventory at the end of September, taking into account only the number of items received and sent out for that month? So solution will be C, right, minus K, because these were the ones that were shipped in to Chicago, and they were the ones that were shipped out. So C minus K is going to be, right, this is my C, stand for Chicago furniture, and this, and K stands for the items that were sent out. So 10 minus 5, right? 10 minus 5 is 5. 12 minus 10 is 2. 5 minus 3 is 2. 15 minus 13 is 2. 20 minus 12 is 8. And 8 minus 8 is 0. So this is what's left at the Chicago's warehouse. Okay. Okay, now now comes matrix product, which means we're going to multiply matrices. So very important information, okay? This is how you can tell if you can multiply two matrices. Multiplication of matrices can only be done under the following conditions. Matrix A, right, the size, and matrix B, the size. So say this is matrix A, it's an n by n matrix. So matrix B has to be a n by p. In other words, the inner numbers have to match. These have to match, which means, right, must match. Yes, it can be done. If these match, you can multiply the matrices. If they don't match, you cannot multiply the matrices. And the answer will be an m by p matrix. So the inner determines if you can multiply the matrices, and the outer will be the answer. Okay, I mean, will be the answer for the matrix, n by p matrix. Okay. If the size of the matrix A is 2 by 3, then matrix B must be, right, must be a 3 by something, right, a 3 by something else, right? This can be any number here, but the inner number must be a 3 for them, I mean, for you in order to do the operation. And the answer, the matrix for the answer will be a 2 by whatever the number is over here at the end. Okay? Solution, again, matrix 2 by whatever the matrix, the size right there is. Example 7. Given the following matrices, state whether the matrices can be multiplied. Okay, so please guys here also try to participate so I can make sure that you understand the concept. Okay, this is, right? Can we multiply the matrices? Let's find out. Matrix C. This is 2 by 3. This is 2 by 2. And this will be a 3 by 2. Can we do A by A times B? Can we multiply matrix A times matrix B? Anybody on the chat, just put yes or no. No, right? Jacob says no, and I agree with Jacob because the inner numbers do not match. Okay, so no, it cannot be done. Okay, first, all right, this is 2 by 3, 2 by 2. This cannot be done. How about 2? B times A. Can we do this one? B times A. Let's give a hint. Let's put matrix B first. Right? Oh, that was for the answer for 1. B is 2 by 2 and A is 2 by 3. Can we multiply them? Anybody? Do the inner numbers match? Right? Yes. So this can be multiplied. And my solution will be a 2 by 3 matrix. How about A times C? So let's list the A matrix is a 2 by 3 and matrix C is a 3 by 2. So again, this one can also be done. Why? Because they match. And the answer will be a 2 by 2. Okay. So now let's go back and actually do the operation, right? So 1 cannot be done, right? No, B times A can be done because it was A times B that couldn't be done. So, right, this one can be done, right? So how are we going to do it? The answer will be a 2 by 3. Okay, now, so these are the steps that you're going to take. Okay, I even color code them, right? So, I mean, color code it because you're going to multiply on the first matrix, right? On matrix B, I'm going to multiply the rows times every column. Okay, so here we go. So I'm going to multiply the first entry here times the first entry here. So it's going to be 1 times 2, right? And then plus 0 times 4. The answer will be 2 plus 0. The answer is 2. So the 2 goes right on that slot. Right? I'm done with step 1. Step 2, then I'm going to multiply the first row times the second column. Right? That's why the inner ones has to match because, right? Because I'm going to multiply this row times every column there until there's no more columns. So my second step is I'm going to multiply the first row on matrix B times the second column on matrix A. So 1 times 0, 0 times negative 2, right? We're going to add them. So this is 0 and this is 0. So the answer will be 0. So 0 goes here. Okay. Now let's do step 3. So I'm going to continue with the same process, right? Because I still have another column to multiply the row times the last column here. So then here's my second matrix. So I'm going to multiply the first row times the third column, which is the final column. So 1 times 5 plus 0 times negative 3. This gives us 5. 5 plus 0, the answer is 5. So the 5 goes here. Okay, now if you notice, we're done with our first row times every column because there's no more columns. So step 4, we're done with this. With our first row, now comes the second row. And I'm going to repeat the process. It's going to be the second row times every column. And we start again from the beginning like I did here in step 1. And again, I color code them. That way you know exactly what I'm multiplying. So 4 times 2, right, plus negative 2 times 4. So it's going to be 8 minus 8. So the answer is 0. So the 0 goes right there. So step 5. And again, after multiplying the second row times the second column, which is going to be in red. So 4 times 0 plus negative 2 times negative 2. So the answer will be 0 plus 4. The answer is 4. So the 4 goes in that slot right there. And lastly, right, at step 6, I'm going to multiply the second row times the third column. And 4 times 5, right, plus negative 2 times negative 3. That will give us 20 plus 6. The answer is 26. So 26 goes on that slot there. Okay. That's how you do multiplication. I have another way to do multiplication, which is very different than the book, but I cannot show you guys here because because I need to do it on paper or else do it on the eraser board. My students, they know how to do it. The other way, which in my opinion is much easier. If you want me to show you that method, please join me during Sunday numbers, and I can show you how to multiply matrices. Okay, a different way. But this is the way the book shows you, and the way most of the instructors also teach it. Okay. So then, right, this is my solution, which is 205, 0426. Okay, now, recall from section 1.1 that a real number 1 is the identity element of multiplication of real numbers. So this means for any real number A times 1 is the same thing as 1 times A, which will be A. In this section, I should have dropped the S there. In this section, an identity matrix I is defined that has properties similar to those of the number 1 property. So here, for example, matrix A times the identity, right, is the same thing as the identity times A, which is equals to A. The identity matrix is a square matrix. By that, they mean it can be a 1 by 1, a 2 by 2, a 3 by 3, etc. It's got to be a square matrix. Okay. So example 9. Say matrix A is A, B, C, D. The identity matrix is going to be 1, 0, 0, 1, right? Because for a 2 by 2 matrix, this is my identity matrix. 1, 0, 0, 1. So find A times the identity, right? Solution, 2 by 2, right? So the answer is a 2 by 2, right? That's a 2 by 2, so the answer is going to be a 2 by 2. So here we go again. That's matrix A. I just use letters because when you do letters, that's when you're proving it, right? That it will work for any matrix that's 2 by 2. And again, I'm going to repeat the same process as before. A, right? A times 1 plus B times 0 is going to give us A plus 0. The answer is A. So A goes there. Step 2. I'm going to continue with the same format, but now I'm going to multiply times the second column. A times 0 plus B times 1. The answer will be A plus B. 0 plus B. The answer is B. So B goes there. Step 3. AB, all right? So now I'm going to multiply the second row times the first column. C times 1 plus D times 0. The answer will be C plus 0. The answer is C. And lastly, step 4, I'm going to multiply the second row times the second column. C times 0 plus D times 1. The answer will be 0 plus D. The answer is D. And here, guys, I just proved it to you that when you multiply a matrix times its identity, you get the same matrix. So in other words, right, so for the homework, right, it's like multiplying 7 times 1, right, is going to be 7. Or a matrix times its identity will be the very same matrix. It's like multiplying by 1, right? But here, when you multiply by the identity, you get the very same matrix. So this proves it for every square matrix. That you multiply the matrix by the identity, you get the very same matrix. Okay, now, inverse says, recall that for every non-zero real number A, the equation AX equals 1 has a solution, namely X equals to 1 over A. So here, guys, right, so what they're doing here, right, if they're solving for X, right, you divide both sides by A here. So X equals to 1 over A. In other words, A to a negative 1 is the inverse. Similarly, for the square matrix A, we consider the matrix equation AX equals to the identity. The equation does not always have a solution, but when it does, we have a special terminology. If there's a matrix, this means the inverse. This means A inverse, which means the inverse of matrix A. So the matrix A times its inverse is equal to the identity. And A inverse is called the inverse matrix. So what's the inverse matrix of A will be, what's the inverse matrix of A will be A inverse. And in a similar fashion, the inverse matrix of B will be B inverse. Okay, now, example 10. Given matrices A and B as follows. Determine whether B is the inverse of A. So you guys, they're trying to determine here if B is the inverse of A. How do we know that? If it gives us the identity matrix, then they're both inverse of each other. Okay, so how can we do it? We multiply the matrices. Okay, let's see what we get. Remember as before, this must equal to that, right? So if we do the multiplication, it's going to give us the inverse, right? And if you follow the concepts as before, it will give you the inverse. Okay, let me show you an example here. So this is the A times the identity will give you the inverse. And here, guys, I do it for the lack of time, but here is where we use the Gauss-Jordan method from 6.2, the one that I covered yesterday. Not yesterday, the last Friday. Okay. So then, right. So in other words, guys, the object here is that I'm going to do this has to be a 0, right? And that has to be a 0. And remember, these have to be 1s. So whatever the identity comes over here to the left, and whatever is here on the right is the inverse matrix. So this is the inverse. This is the inverse, negative 3, 1, 2, negative 1/2. It's the inverse of the matrix 1, 4, 2, 6. See, that's my inverse. Okay, now also for a 3 by 3 matrix, A, right? A. And the inverse, again, I'm trying to put the identity over here on the left by using the Gauss-Jordan operations, and then whatever I have on the right will be my inverse. Maybe for next time, I will work this out for you, okay? And maybe for next semester and stuff when I do this very same PowerPoint. But this takes a good 5 to 10 to 10 minutes to actually go over it. That's why for lack of time, I didn't want to do it here in this PowerPoint. But if you come see me doing Sunday numbers or one of the tutors, they'll be more than happy to show you how this is done. Okay. So after you do all the operations, this is your inverse. Right. So the inverse is going to be, this is the inverse. Okay. Now, if you guys know how to input the matrix in the calculator, but it has to be, I believe, I can do it in a T83, T84. You guys can actually plug it in there, plug in the matrix, and just hit the inverse button or the inverse key, and they'll give you the matrix automatically. And perhaps some of the tutors can show you how to do that, because it's always wise to know how to use a calculator, how to do the matrix, so you guys can check your work. But on every exam that instructors give, you have to show all the work. All right, so it's always good to know what the answer is, right? And this way you know how to get the answer, but you have to show the work. Okay, now, but for a 2x2 matrix, there's an alternative way to find the inverse, but this only works for a 2x2 matrix. Okay, so I'm going to show you this method here. So instead of using the Gauss-Jordan method for a 2x2, this will be much easier. Okay, so for the inverse of matrix A, you're going to do 1 over the determinant. The determinant means you multiply A times D minus B times C, right? And then what happens is that these two, right, the A and the D, you switch, right? The A goes to where the D is, and the D goes to where the A is, right? You switch these two here. And the B and the C, all you do is switch the signs. That's what it means, right? This will be switch the signs. So again, you switch the A and the D, and you switch the signs on B and the C. So for example, find the inverse of matrix A. Matrix X is 1, 2, 4, 6. So the inverse, right, is going to be 1 over 1 times 6 minus 2 times 4. If you notice, this will give us 6, right? 6 minus 8. Right, so this will give us 6 minus 8. This will be negative 1/2. And then, right, these two, you switch them. The 6 goes to where the 1 is, and the 1 goes to where the 6 is, right? You switch them. And these two, the 2 and the 4, you do is switch the signs. Right, so this is negative 1/2 times 6, negative 2, negative 4, 1. And now this is like a scalar, so you multiply the negative 1/2 times every element in the matrix. So negative 1/2 times 6 will give us negative 3. Negative 1/2 times negative 2 will give us 1. And negative 1/2 times negative 4 will give us 2. And negative 1/2 times 1 will give us negative 1/2. So this is my let me go back. That was my, okay, let me go back here. I'm sorry about that, guys. Let me go real quick. So that was my answer, guys. This was my solution. So this is the inverse. And in my opinion, this method is much easier than doing it by using the Gauss-Jordan method. But it only works for a 2x2 matrix. For a 3x3, you're stuck by doing the whole work. Okay, and I'll see if I can on my next PowerPoint that I do next semester. Hopefully, I'll be able to include it, but it's going to take a little bit like some time. Anyway, guys, that's it for my PowerPoint. I hope and I mean, I just hope that you guys understand it and it can be useful. If you want an actual copy of the PowerPoint, send me an email at aesasi@epcc.edu, and I'll be really happy to send you the copy of this PowerPoint. Thank you, guys.
All right. Does anyone have any questions for Mr. Azasi? If not, let me go ahead and I'll invite y'all to next week's TVE. Just give me just a second. All right. Oh, there it is. Okay, so next week, with the TVE link, we're on November 5th. We're going to have Veterans Affairs and Veterans Resources at 1 p.m. And then for Math Happy Hour at 3 p.m., we're going to have, for Math 1314, we're going to have linear and nonlinear systems. And for Math 1324, we're going to have a review for exam 3. Please don't forget to sign in for attendance. The code word is excited. And we hope you have a wonderful weekend. Thank you for coming.